you all for having me in this presentation. I'm Dr. Vipul Agrawal, and I'm the first author for the paper All Optical Parity Generator and Checker.
Sir, kindly turn on slide share mode.
Okay.
Yes, sir.
Sorry for the delay. I'm more accustomed with Teams. Okay. Now, my paper is all about all optical parity generator and checker based on quantum dot semiconductor optical amplifier. So, in this paper, we have worked on parity generator and checker, which will be working only on optical domain. There will not be any conversion between electronics to optical conversion. And it is a simulation paper, not an experiment paper, and we have simulated the proposed circuit at the data rate of 200 Gbps. So I will be moving this fast as we have only 12 minutes. So this is the abstract. What we have done in this paper is we have simulated optical parity generator and checker at 2200 Gbps. And as you know, basic building block of a parity generator is XOR logic. So XOR logic we have designed, and then same we have implemented to design parity generator and checker. Now the point to be noted here is data rate is 200 Gbps, which is very high. Usually the speed data rate is around 50 Gbps, but since we have used quantum dot, we have managed a data rate of 200 Gbps. There have been paper written by the authors which is above 500 Gbps based on quantum dot. In our parity generator utilizes 3 XOR, 2 XOR logic for parity generator and 3 XOR logic for checker. So this is the basic logic, and I think you all must be knowing this schematic. So this is the basic building block of parity generator. In short, I will explain that whenever the input number of bits are odd, then parity generator will add 1 bit to make all bits even. And at the receiver, the number of bits are counted, it should be even. If it is even, output will be 0, means no error. If it is odd, then output will be 1. So this time we are seeing at the parity generator. So you can clearly see whenever there is odd number of bits, for example here, extra bit is added to make all 4 bits even. Now this is the checker where whenever 1 comes means it's an error. 1 means 4 bit as is having odd number of 1. So at the transmitter we have ensured that and we are sending even number of bits, but at the receiver if you are receiving odd number of bits means error has emerged, and that's why this checker is checking that it's an error. 0 means no error, means odd number of ones. So we have used semiconductor optical amplifier for the logic gate design. Now in optical communications we need a non-linear characteristics to design optical logic gate. So we all have heard about non-linear fiber, but non-linear fiber also there have been gate that is designed using non-linear fiber optical fibers, but the length of those fibers is like 1 kilometer, 2 kilometer. So it is really impractical to use such a highly non-linear fiber, and also a non-linear fiber will add extra distortion as well as dispersion also. So now the engineers have switched to semiconductor optical amplifier for the design of logic. But this logic SOA suffers from a problem that it has got unequal amplification. So you can clearly see on the below figure that data is sent before SOA, but after SOA what you are seeing is unequal amplification. This is because of gain saturation. Now what it is happening is this Input data, when it interacts with electrons in the conduction band, stimulated emission occurs, and which would lead to depletion of electrons in the conduction band. Then the next input bit, if the next input pulse comes because of the depletion, the next pulse will not be amplified. So the pulse you can see is amplified unequally. So in this work, first of all, we have implemented quantum dot so that we can increase the data rate. Secondly, we have used 200 Gbps, and we have used quantum dot in the upper and the lower arm of Mach-Zehnder interferometer. So in the upcoming slide, I will show you Mach-Zehnder interferometer. So what is quantum dot? Quantum dot is a nanometer structure. It is nanometer structures, and it is very difficult to fabricate. But what is the advantage? Is faster gain recovery. As I told you, in the conventional semiconductor optical amplifier, due to depletion, there will be sudden drop in the gain, and therefore unequal amplification takes place. So we cannot use SOA for high data rate. But if we implement quantum dot in SOA, that problem can be solved because quantum dot has a wetting layer which is having extra electrons. So whenever there is a depletion, wetting layer provides the extra electrons to ensure that electrons are always present in the conduction band for stimulated emission. So these are the semiconductor optical amplifier characteristics. It is made of indium gallium arsenide, and this will explain you the reason why there is unequal amplification. You can clearly see there is a drop in the gain. This has happened because of the input injection of input pulse. So why there is a drop? Because input pulse has depleted electrons in the conduction band. So there is a drop in the gain, and this is called a non-linear characteristics. Now remember, because of this drop in the gain, there will be a phase shift introduced, which is called self-phase modulation, which can be used in the design of logic gate. So this is the concept of amplification principle. So remember here SOA, the full form of SOA is semiconductor optical amplifier, but here we are not using it as an amplifier, we are using as a non-linear element. So what we have seen, electron is excited, and then it comes in the interaction with the input beam, incoming beam, and then it further drops, and photon is released which is having the same wavelength as the input beam. So the stimulated emission is taking place. So this is the structure of SOA. Now what we have done is, this is the conventional SOA, but now if we can use quantum dot SOA in the active region, then we can overcome the limitation of slow carrier recovery, which leads to unequal amplification of pulses. So this is the gain saturation formula. If you notice, as P approaches PS, G will reduce. So this formula shows that P should always be less than PS to have a significant gain. If P becomes comparable to PS, then gain drops. That means unequal amplification. So these are the basics of population inversion and all. Because of lack of time, I am not going into the details. Any questions you can ask me. So this is the concept that we have used. I will explain a little bit more how phase is introduced, as I explained. So our XOR logic, which is used in the parity generator, uses semiconductor optical amplifier, which exploits the cross phase modulation. So what is cross phase modulation? Here you can see a continuous wave signal and data bits are multiplexed in the SOA. So whenever data bit is 0, there will be no depletion of electron because input pulse is 0. So the phase introduced in the continuous wave will be 0. But whenever data bit is 1, there will be a depletion of electrons in the conduction band, and now that will cause change in the refractive index, and that will introduce pi phase shift. Now remember, this phase shift will help us to get constructive and destructive interference. So for destructive interference, we say 0 is obtained, and for constructive, 1 is obtained. So here there is a way to improve the SOA gain. We are using quantum dot technique here, and we have successfully simulated at 200 Gbps. So this is the SOA-MZI. This is the our XOR logic. So if you see, I will explain you through this diagram. Here what we can see is that there is a phase shift introduced in continuous wave laser. Okay, and this continuous wave laser is met at the output, and in the output, constructive and destructive interference will take place. So whenever XOR logic 1 is required, we ensure that two waves coming from top and bottom interferes constructively. So we say 1 is obtained, and if they interfere destructively, we say 0 is obtained. So the phase shift is designed in such a manner that XOR logic table is fulfilled. So you can clearly say whenever 0 0 is there, it's destructive. So as you know, for input bit 0 0, output should be 0 for XOR. So means destructive. For 0 1, we are ensuring that continuous wave have a phase shift such that they overlaps constructively. So we obtain 1 here. So for 0 1, 1 is obtained. So by precisely setting the phase shift in the continuous wave and then making this continuous wave interfere as per our requirement for XOR logic, we have designed the gate. So this is the verification of our output. You can clearly say whenever input bit is 0, output is 1. So here you can, whenever input bit is different. So these are the two input. So here both our input bit is 1 1, that is same. So output is 0. Here 1 0 means input is different. So output is 1. That is the characteristics of XOR. Input different means output 1. Input same means output 0. So here also input is same, so output is 0. This is our parity generator design. So as I told you, simply I have kept the XOR logic that I have explained just now in one gate and this gate. And this is our checker. So checker will have 3 XOR. So we have simply kept the 3 XOR blocks here. So this is the parity generator output. As I told you, for parity generator output, if the input bits are odd, then 1 bit is automatically added. So you can clearly see 1, 2, 3. These are odd number of bits. So parity generator have added 1 bit. This is already even 1 and 2. So nothing is added here. So this is the eye diagram, which is very open eye diagram. This is the parity checker output. So you can see some distortions now have come because it has traveled all the way. Now in parity checker, whenever there is an even number of one, output should be 0. So let us see clearly here, 2 ones are there, that is even. So output is 0. Whenever there is odd number of 1, 1, 2, 3, odd. So output is 1. Means this is an error case. So clearly our circuit is working properly, and this is the performance parameter of our proposed XOR logic. We have simulated at 200 Gbps. Quality factor is low, but considering the fact that data rate is very high, it is still above acceptable limit. And below is the extinction ratio. In eye, we got a very highly opened eye also.
Yes,
This is
sir.
the conclusion. Yes, sir.
I request you to, sir, please kindly wind up because we are.
I reached the conclusion, sir.
Okay, sir. Thanks so much.
So this is the conclusion, and in this conclusion we have mentioned about the performance parameters, which clearly shows that it can be implemented practically. However, the drawback of this proposed work is that quantum dot is very difficult to fabricate, and therefore uh, it is used very rarely because it will take a lot of time to fabricate, and commercially producing a quantum dot based semiconductors is difficult. So that is the drawback. However, if you see the advantages, it has successfully overcome the low data rate limitation of conventional SOA. So these are the references. Thank you.
Thank you so much, sir. Any questions?
Yes, Dr. Karan. Dr. Vipul, thank you very much.
Thank you, sir. Thanks a lot for hearing me, sir.
It will be good if you are going to talk a little about the tool, your simulation tool.
Yes, yes, sir. Yes, sir. I have used OptiSystem software, sir. OptiSystem software is being designed by OptiWave company, OptiSystem 18, sir. So in the paper, I have mentioned that OptiSystem 18 has been used to simulate the overall XOR logic and then parity generator and checker, sir.
Thank you very much. Thank you.
Thanks a lot, sir. Thanks for